Okay, thank you very much for giving me the opportunity to talk to you. Let's see if I can do this. Do you have the first slide? Yes. All right, so this is, okay, so I'm going to talk about how we first have to feed a planet of 9 billion people, and that really ultimately comes from energy, and it's very related to climate change. So I'm going to first talk a little bit about some recent data. This is the global temperature of the land and sea surface, and what I want to point out is it's only since about 1970 where most of the increase in temperature has occurred. Already we're beginning to see changes in weather patterns over the last several decades. We see hotter summers demanding more irrigation, but as we irrigate more, the water aquifers around the world are being depleted. We also see increased droughts, heat waves, crop failures in the western part of the United States, where every year now nearly record forest fires and rising seas. So one sees tens of millions of climate refugees being created in the coming decades. I should also remind you of something in history. The UN goal is to stay below 1 degree warmer than we are today. But if we look back in history, in the last warm period, which is about the same temperature as the UN goal, the average sea level rise, as a matter of history, not a climate model, was 6 to 9 meters higher. We used to think this would take 2,000 years, but now we think it perhaps would occur in just 200 years. So the dramatic change is due to a newer understanding of how glaciers slide off of Greenland and Antarctica. Now, if we say, what do we need in order to keep below the UN goal of 2 degrees, it's actually outlined by those blue lines in the lower part, and so this is time 1980 to 2100. But I want to draw your attention to the vertical axis where you see 0. 0 means all carbon greenhouse gas emissions from transportation, electricity, agriculture, process heat, home heating has to go negative in order to reach this goal. And if you look at this goal as a more realistic version, we see we're heading towards perhaps 3.5 degrees or more. So, just to remind you what that goal is, the cumulative emissions has to be below 2,900 billion tons of carbon dioxide. Again, 3/4 of all these emissions have occurred only in the last 65 years. This is something ascribed to the father of Taoism. If you don't change direction, you will end up where you're heading. But I should also remind you of something else that's not widely appreciated. Once the carbon is in the atmosphere, it circulates. Half of it gets very quickly absorbed by land and ocean within 5 or 10 years, but the rest of it circulates for a very long time. How long? About 10,000 years. So don't think 2100 and whether we're going to have our problems over or not. Think 2100, 12100. So this is effectively forever. All right, so let's talk about opportunities to feed a growing planet and rising prosperity. First, this is a summary of land use. That brown on the upper part is land. The orange is habitable land, and of that orange habitable land, that means not mountains, not Gobi deserts and things like that, half of it is already under agricultural production, either direct crop production or land for livestock. So already we've geoengineered half the habitable land of the world. And so how are we going to improve feeding a hungrier and more prosperous planet? This is where some very exciting science comes in. This is one example, a startup company called Pivot Bio. And in this company, they are actually putting first into additives to the soil, but later onto the seeds themselves, microbes that enter into a symbiotic relationship with the roots of a plant, just as in legumes, you can have these microbes interacting with the plant to fertilize the plant, actually grab nitrogen out of the atmosphere and use that as the needed nitrogen for the plant. And this experiment is more than an experiment. It's finishing field testing and will be marketed within the next year. So this is self-fertilizing corn. And with self-fertilizing corn, you eliminate, and if you can do this for wheat, for rice, and many other staples, you can eliminate about 2% of greenhouse gas emissions due to ammonia production for urea and also fertilizer runoff. So it's a very significant part of the solution. But let's talk about geoengineering of the planet. Most of the carbon of the planet exists in the form of plants. That's the green stuff you see. And only a very small fraction are animals, that is, things that are not bacteria or fungi. And if you blow up this section that are animals, what you find out is that most of the animal mass is in the form of things like spiders, insects, millipedes, crustaceans. Then I draw your attention to, wait a minute, let's see. Yes, the mammals. And where's the biomass of the mammals? You see three entries: livestock, humans, and all the rest of the mammals of the world. And it turns out that livestock and human biomass is 96% of the entire animal biomass, of the mammal biomass. So again, this is significant geoengineering. We've bred animals over the last tens and hundreds of years. So beef cattle, the full circle of each of these is the natural lifetime of the animal, but the little sections in red are the time before slaughter. Beef cattle are slaughtered 18 to 24 months after birth. Pigs, only 22 to 26 weeks. Broiler chickens, 40 days. Turkeys, 14 to 16 weeks. When pigs are slaughtered, they actually weigh 280 pounds. So these are animals that are actually growing very, very rapidly. These are domestic turkeys, the kind you find in a supermarket at 12 to 14 pounds without the head and the guts and the feet, but just the meat part. But these animals are not what you find in the wild. Indeed, the farm-bred turkeys are so breast-heavy they can't survive adulthood, and they can't even mate. They have to be artificially inseminated. Now, you compare this, oops, I lost my joke slide. If you look at wild turkeys, they look very, very different, but never mind the joke. What this has prompted scientists to do is to begin to derive meat substitutes, things that taste and cook like meat, and in fact, in blind taste tests, excel the taste of meat. Impossible Burgers and Beyond Meat are two examples. I happen to know the founder of Impossible Burger. He was a Howard Hughes medical investigator who invented the gene chip. He stopped doing his biology to actually do this. And it tastes like blood because there's a hemoglobin-like molecule that you find in a vegetable that you put in the meat, and when you cook it, it sizzles like meat because there's a myosin-like molecule that releases juices. So this is real biochemistry, all derived from vegetables. Now, the good news is renewable energy, notably wind and solar, have plunged in cost, down by factors of 5 and 10, and the expectation is costs will actually continue to decrease until it's about 2 cents a kilowatt hour at the best sites around the world. So I'm not talking about solar energy in Great Britain or Northern Germany. I'm talking about solar energy in the Middle East, in half the United States, places like that. But the full cost of renewable energy is just not the levelized cost. In fact, renewable energy has to become twice as cheap as fossil fuels, because when you get to be 50% or more of the cost of renewable energy, you also have to have backup generation capacity, energy storage, a very enhanced transmission and distribution system. As an example of this, you need a very complex electricity distribution system. We don't currently have the means to do this, but before, energy storage. Okay, here's my picture of my favorite battery. Here it is. When the way this battery works is the following. When the wind is blowing, we knew this several hundred years ago, you pump water from under the ground to a tower. When you need the water, you open up the valve. So the energy is in the stored water because you've used the energy when you have the renewable energy. Now, this idea of pumped storage remains the least expensive energy storage we have in the world by about a factor of 10. It's 10 times cheaper than the current batteries. And if you look at the pumped storage in the world, I draw your attention to China. By the end of 2020, they will have added 40 additional gigawatts of pumped storage, and their plans are by the end of 2030 to be at 90 gigawatts and several hundred gigawatt hours of power, of energy. And so China is actually on target to have more pumped storage than all the rest of the world combined. Now, the very complex energy systems require unstructured machine learning to manage this automatically. Here's an example of unstructured machine learning where they've programmed a computer to recognize patterns. It played itself over and over again. It learned from its successes, learned from its losses, and it then beat the world champion Go player. It was being televised. This is the Chinese champion. It was being televised until midway through the first match where they cut the feed because the player started to cry. Now, the same people who programmed the machine to play Go are now helping the Great Britain's national grid system to actually automate their electricity and to manage a more complex distribution system. Let me talk about electric vehicles. Now I'm going to show you two predictions, one in dark blue, the other in red. They differed by 2 years. This goes from about 2015 out to 2040. Now, why did the forecast increase so dramatically in only 1 year? Was it a big breakthrough in batteries, something else? And the answer is it was not a breakthrough in batteries. To actually help you understand what the change was, I take you back a century. This is Easter morning in Fifth Avenue in New York City in the year 1900, and you see all horse-drawn carriages. 13 years later, you see Easter morning, Fifth Avenue, you see only one horse-drawn carriage. The rest are automobiles. This is a very, very fast technological sweep through cities. The transition required many, many new things, an oil and gas supply chain, paved roads, repair shops, all the other infrastructure. But there was one significant driver, and that was an environmental pollution problem. What was the pollution problem? It was 1,600,000 horses in New York in 1880 producing 3 to 4 million pounds of horse manure a day. And it was piling up everywhere, and they couldn't move out of the city fast enough. So along came a cleaner solution. Now let's fast forward to this century. This is Beijing on a bad air day. We're finding out that particulate matter, PM 2.5, is especially deadly. And in the larger epidemiological studies, more are being conducted today. You find that for every 5 micrograms per cubic meter of PM 2.5, there's an 18% higher chance of getting lung cancer. Okay, what's the average air in Beijing? It's about 76 micrograms per cubic meter. The average air in Delhi is about 300 to 400 micrograms per cubic meter. So that's the equivalent of about 4 packs of cigarettes a day, and everybody smokes from day 0. You don't go inside and hide from it because home ventilation purification systems do not filter out PM 2.5. And so these results are so new that the World Health Organization guidelines that they consider clean air is 10 micrograms per cubic meter. That's only a 36% higher chance of getting lung cancer. So this, we're expecting, sadly, that tens of millions of people per year will be dying of these diseases in the coming just few years. It's now passing 6 million deaths per year. All right, what about electric vehicles? Well, batteries are improving dramatically. The new generation batteries, there are many researchers working on that. I've started to work on that with a colleague of mine, Yi Cui, at Stanford. We're working on silicon and, most importantly, metal batteries, metal lithium and sulfur batteries with these higher energy densities. The eventual goal we really want to achieve is that you can go 100, 130 miles in 5 minutes of charge for a 300-mile range. Once you get this fast charging battery, then you don't need charging stations except in service stations. You don't need it in your homes. Most people are too poor to own garages anyway. And if you can get this in a $20,000 car, people will buy these because it's simply a better car. Now, clean electricity, I said before, is expected to be 2 cents a kilowatt hour. And at 2 cents a kilowatt hour, the cost of electricity to make hydrogen is only 1/2 the current price of hydrogen that's being paid commercially today. And so there's new opportunities in electrochemistry. Here's another bit of research I am doing with Yi Cui and a graduate student, Jung Lee, and it's inspired by how the human lung actually takes in oxygen and gives it to your cells and takes out the waste of metabolism that's carbon dioxide, and you exhale the carbon dioxide. And so the idea of this is that suppose you had air, in the lung you have air, in this case, suppose you have water on one side of this very small membrane. It's a plastic membrane that does not like water, and it's got a lot of porous holes. So the bottom picture shows what the membrane looks like. You put catalysts on this membrane, and what happens in this electrolysis where hydrogen and oxygen normally bubble out, if you take a microscopic view of the catalyst, after a little while you begin to form oxygen and hydrogen. They're very low solubility, so the molecules run around and form a bubble. The bubble grows. You have to supply energy to the bubble in order to counteract the surface tension. The bubble grows even bigger, but before it's released, it's actually blocking many other catalytic sites. So the moral of the story is bubbles are bad. So how do you eliminate bubbles? You actually have this porous membrane, and when the oxygen and hydrogen look around, they can go a few molecules distance away and escape as a gas, or they can form a bubble. So they always choose to escape as a gas. What we find is that for the same amount of energy, the reaction rate is 4 to 5 times faster. It's agnostic of catalyst. You invent a better catalyst, this just gets better. So that's something we're very, very excited about. There's something else that we're excited about. This can actually be made very compact because the cost of an electrolytic plant is actually half the price of producing the electricity would be the physical footprint of the plant. You can make tiny spacers in here. This, on each side, there's the catalyst, and the hydrogen and oxygen escape. And so now you get very, very high density, and so perhaps the footprint could be shrunk by a factor of 5 or 10. Now, let's go back to the carbon emissions. We have to stop emitting carbon. The first thing is you've got to actually start with all the sources of emission, which include not only electricity generation, but transportation fuels, cement, chemicals and plastics, iron and steel. Cement is 5% of all carbon emissions, but as China continues to develop, as India develops, as sub-Saharan Africa begins to build cement, steel, plastics, and cement, as I said, cement, all these things will actually increase, as will transportation. Now, we need to get to negative emissions. How do you do that? Well, the global emissions in 2017 was about 39 gigatons of carbon dioxide, but just plant life in agriculture plus pasture land actually captures carbon dioxide from the atmosphere and turns it into plant material at twice as much per year, but it all circulates. And so If you just let me just 1 minute? I'm just going to conclude by saying that they cut me off prematurely. Does that mean that bleep means? Okay, so I just want to conclude by saying the whole idea is to turn carbon dioxide and water back into chemical fuels, beginning with hydrogen, carbon monoxide, and build liquid hydrocarbons. The reason you want to do this is because you can ship liquids around the world. If you ask how much does it cost to ship crude oil and store it halfway around the world, the answer is about 2 cents a gallon. So long-distance transportation on a supertanker is almost free. So if you can make energy in the cheapest places, ship it around the world, you will have your ideal chemical battery. And so I just want to say that this is the Earthrise picture from Apollo 8, and the astronaut who took the picture says, we came all this way to explore the moon. And the most important thing is we discovered the Earth. And look around, the moon is not a good place to live, Earth is a good place to live, and it's black everywhere else. Nowhere else to go. And so I think, going back to the theme, we do have a moral responsibility to protect the most innocent victims of climate change. And those are the poorest people in the world who had nothing to do with this, and those children yet to be born. And there's an ancient Native American saying said, we do not inherit the land from our ancestors, we borrow it from our children. Thank you.